Hi guys, welcome to this page of the notes, and before we go ahead and start to take a look at solving exponential inequalities, I want to take a look at another kind of problem that you guys are going to see when it comes to exponential equations, and that has to do with compounding interest. Turns out exponential functions are a great way for predicting interest accrued on a principal amount of money that you may save depending on what the interest is. So, this equation, hopefully you recognize this formula, you recognize from previous math classes. I am sure that you've seen the compounding interest problem before. If you haven't, don't worry, I'm going to go through it with you here and kind of explain how it works. But this should look very similar to something we actually did in section 1 of this chapter. Let me show you. We have already looked at two equations, exponential growth and exponential decay. And let me remind you what those looked like. The exponential growth was a equals a naught times 1 plus r raised to the t power. So that was exponential growth because it's 1 plus the rate. A is the final amount, a naught is the initial amount, r is the rate, and t was the time based on the problem, right? It could be minutes, seconds, weeks, years, whatever. And then we had the exponential decay, which was a equals a naught 1 minus r to the t power. Right, so we've already looked at both of these equations, exponential growth and exponential decay. And hopefully what you see looking at this formula is that it's very, very similar. The difference here being now we've introduced this variable n, which I'll talk about in just a second. But if you were to take away the n, right, essentially what you've got is this guy right here, the exponential growth. So that's exactly what compounding interest is. Compounding interest is exponential growth. The reason we need the variable n is we just need to know how many times is the interest being compounded, and that's all that n does for us. So these two equations, these two formulas, exponential growth and the compounding interest formula, are almost identical. They look exactly the same except for this variable n, and I use a p here. And the reason that we use a p is because in finance, rather than saying the initial amount, in financial terms we call it the principal. What is the principal amount? It's the initial investment. How much money do you put into the account to get it started, right? We call that the principal. So instead of using a naught, we'll just use p for principal, but it's still the initial amount. So very, very similar equation to the exponential growth. It's just now we have this new variable n. So let's talk about n. I've already gone over this. A is the amount in the account after t, which of course will be in years. R is the rate. P is the initial investment. We call it the principal. So here we go. We have n. Compounded n times per year. And that's the idea with n. N is always going to be in terms of how many times it's compounded per year. Let me give you a couple of examples. Let's say that I have interest that is being compounded weekly. Well, if you're compounding interest weekly, I need to know how many times that interest is compounded in a year. Well, if it's being compounded weekly, how many weeks are there in a year? There's 52 weeks in a year, and so n would be 52. If you were going to compound it monthly, again, n needs to be for an entire year. If I'm compounding the interest monthly, how many months are in a year? Yeah, there's 12 months in a year. What if we did quarterly? Well, if you were to compound interest quarterly, how many quarters are there in a year? Well, of course, quarter means 4, so there are 4 quarters in a year, and in this case would have to be 4, right? If we were to do it annually, of course, would just be, right, annually means once a year. In this case, n would then be 1. All right, so that's the idea. N is going to be how often is the interest compounded, but you have to figure out how many times that'll happen in a year. Of course, if interest were compounded daily, you'd have 365, stuff like that. So you can easily figure out how many times interest is being compounded, but it's got to be in a year. All right, so let's go ahead and do the problem then that I've got for you guys. Make sure we can still see my formula. There it is. And here's our problem. An investment account pays 4.2% interest. That's annual interest. It's compounded monthly. If $2,500 is invested in this account, what is the balance after 15 years? All right, so you're going to put $2,500 into an account paying 4.2% interest, and it's going to be in there for 15 years. Trust me, if you're investing money into an account, generally for retirement or something like that, it's not going to be in there for a couple hours or a couple of days. Essentially, they tell you whatever money you put into a retirement account, into an investment account, just forget you put it there. You put it in and you let it stay in there for many, many years until you're ready to retire. So 15 years actually isn't even that long, right? Sometimes the average sort of a lifespan for an employee in the workforce is probably somewhere around 30 years, 30, 35 years, something like that. So 15 is actually only half that amount of time. Anyway, here's the idea. We need to go ahead and set up our formula given the information we have in the problem. And remember from the previous section, R has to be a decimal. I've given you a percentage, but do not put the percentage in the problem. It must be as a decimal, not a percent. All right, let's go and get this guy set up. A is my final amount. That's what I'm trying to solve for. P is my principal. I know what that is. It's 2,500. 1 plus R over N raised to the NT power. All right, here we go. Let's do a little plugging and chugging. A is going to be equal to, my principal amount is 2,500. It's going to be 1 plus. My rate is 4.2%. I move the decimal point 2 spots to the left. So I get 0.042. That's all going to be divided by N. Now here's what they tell me, right? They tell me that it's annual interest compounded monthly, but I need this to be for an entire year. So how many months are there in a year? We actually did that one up above. There's 12 months in a year, so you're going to need N to be 12. N shows up in 2 places, so don't forget to put it in there twice. And then, of course, my T, well, we're going to leave this money. I want to know how much is in the account after 15 years. All right, seems like a really, really long time to leave money in the account. Unfortunately, I fear you're going to be a little bit disappointed by how much money is in the account after waiting for so long. Granted, it's free money. You don't have to do anything. All you do is put money in and then you just forget about it. You come back 15 years later and there's more money in there than you started with, which is awesome. You didn't have to do anything. It's just accumulating interest on its own, which is a great way to make money, but it doesn't happen quickly. So let's see what happens here. First thing I'm going to need to do, don't forget the order of operations. You don't want to plug all this into your calculator once. It'll mess up the order of operations. I'm going to go ahead and take care of what's in the parentheses first. So 0.042 divided by 12, I wind up with 1 plus. Don't round. We'll wait until the end to round, so don't do any rounding. Make sure you keep all your decimal points. 0.0035 raised to the, I'll also multiply 12 by 15 and get 180. All right, we'll go ahead and do what's inside the parentheses. So I'll add 1 and 0.0035. Now I'll do 1.0035 raised to the 180th power. Again, don't round. We'll save any rounding for the end. We don't want to propagate rounding errors through our problem, so we'll just wait to do it at the end. Make sure you keep all your decimal places. I get 1.87. Again, I got a calculator here. Let's see. I get 5, 5, 4, 6, 4, 6, 7. Again, that's what I get by doing 1.0035 raised to the 180th power. I now multiply these guys together, and here's what we've got. After 15 years, my initial investment amount of $2,500 has grown to $4,688.86. Now, here's what's awesome. You've made, without having to do anything, you've made about $2,100. You didn't have to do anything. All you did was you put your money in, you forgot about it for 15 years, you come back and there's an extra $2,100 in there. However, you waited 15 years and your money didn't even double. And here's the point. You guys are going to want to begin to invest. If you have any hope of retiring, you're going to want to invest early and invest quite a bit, right? The more money you put in, obviously the more money you're going to make, and the longer you're able to leave your money in there, the quicker the more will be there when you do retire. You do not want to wait until late in life. The money doesn't grow that fast. And also what they'll do is when you're younger and you just kind of get started, they'll put your money into an account that is a little bit riskier. Generally, they'll invest your money in things like the stock market and investing into stocks and shares and stuff like that. It's risky because, of course, you run the risk of losing everything. However, generally, the stock market will pay bigger returns than 4.2%. Then as you get older and get closer and closer to retirement, they'll begin to take your money, your investments out of those more risky areas and begin to put them into things that are much safer. They'll pay much smaller percentage in interest, but there's no risk then of losing what you've already made. So anyway, the idea here is you want to go ahead, if you have any hope of retiring, you want to get started early. As you can see from this problem, it takes a while for that money to grow. And so if there's going to be anything in there for you to live on, you'd want to get started as early as you can. Anyway, this is a great example of how exponential functions work, especially in the financial district and when it comes to economics, especially with the compounding interest problem. All right, guys, head on over to the next page of the notes. We'll take a look at solving exponential inequalities. I'll meet you guys there.